Okay, let's go ahead and start. So, today we're actually going to get into, I'm just going to be covering the notebooks on the polynomial regression, the learning curves, and the regularization. So it's going to be the stuff pretty much directly on the assignment that you should be working on. So, yeah, just a reminder about that. We've got our next assignment is due on Friday here. So I've seen looks like a lot of people have started working on it, to make some progress. That's good. So I did get back. I think I maybe have one or two people that haven't given me some preliminary idea on the project, the class project. So, but yeah, if anybody's watching this or still hasn't updated their class project to indicate which data set that they want to use for it, you should go ahead and you should get that done. So I tried to look through everybody's that I'd gotten last Friday and this weekend. So, before I jump into the stuff today, I mean, one more thing about that. I would encourage people to, keep that in mind. So, people do better if you do a little bit of some work on that, like every week. So, I don't know if I'll make it like an official kind of requirement, but you ought to make it like a goal to, like make at least one commit each week or so from now till it's getting closer to being due, just so that you have it in your mind, that you're thinking about and working on it. So a good thing to do this week would be, if you've gotten your data set, you wrote up a little bit about what you're planning on doing, to actually create like a notebook, if you don't have one already. And get your data loaded in, so you can start doing some data exploration. So that would be kind of a good goal, for this week for your project. Get started, make sure you have a notebook in there that's running, that kind of thing. Okay, but yeah, the rest of today and Thursday we'll be going through the notebooks on Unit 6. So these will be pretty much directly relevant to the assignment. And maybe I'll if anybody has any questions about the assignment, let me know. Probably sometime in the last 5 or 10 minutes I'll bring up the assignment directly. We haven't actually looked at it yet in class, and see if there's any questions that people have that want to ask to clarify for the third assignment here. So, all right, let's get in here. So, I haven't tested these here. Make sure these are still running okay. All right, this notebook might take a little bit of time to run. Okay, so just a little bit of a recap from last time. We had gotten through, I did it relatively quickly, but we had talked about linear regression, the idea of a cost function, and then, the cost function has a couple different names: a cost function, a fitness function. It's a function that usually we're trying to minimize. So you can take a whole course, on doing optimization in computer science. So it's a type of optimization problem. So once you define a cost function like we did for linear regression, you can use different optimization methods to find the minimum cost, so to find the best set of I'll usually refer to them as the theta parameters, but those are really the slope, the intercept, and the parameters for each one of the features that you have. You're going to have one parameter for each individual feature of a data set that you're trying to fit a regression to. Plus, you always have to have one extra parameter to fit basically the intercept is the way I always think of it mentally in my mental model. So in the simplest case, you only have one feature, so you have one parameter which corresponds to the slope of that line, but then you also have to have a second parameter which corresponds to the intercept. And as we showed last week, we use the mean squared error is going to be the cost function we'll pretty much use for most of the stuff in this class to do regression problems on. It will give you a nice cost function that will have the property that if you find the slope and the intercept, or the theta parameters that minimize it, there will only be one minimum of that because of the shape of it. So we showed that last time. It's a parabola if you just look at it in for one dimension, one feature. So in higher dimensions, it'll still have that same property. There will be exactly one location where that will minimize, that will give you the smallest cost if you can find it. So, and there are exact methods to find, when you're working for a linear function, there are exact methods using the thing that we showed last time, but we'll usually use an optimization method, which is really an iterative method that does rely on being able to take the derivative, but it will take small steps towards smaller and smaller costs until it gets as small as it can find it. Okay? So those are kind of the essentials of gradient descent and some of the stuff that we talked about last time. So for the actual third assignment, we're doing something known as polynomial regression. So it surprises people sometimes to find out that you can actually use the same method, the same cost function, and the same sort of optimization, like gradient descent, to fit a nonlinear model. So instead of a line fitting like something with a square, a quadratic, or even higher power. In fact, in the assignment that you're working on right now, the mystery function that you have some data for, probably it's much higher than like squared or cubed, so it's like probably a 6th or 7th or 8th power in some of the terms there of the data that you're trying to fit regression models to. Okay? So, yeah, we'll come back to that. So we'll start with kind of the simplest idea. Let's say that we have a function that looks like this. Okay, so and this is exactly kind of what we're doing in your assignment here. So if you're trying to fit a regression model to a real set of data, I mean, you'll never really know what the reality is that's actually generating that data, and there, depending on what's generating that data, it might not have something that's the reality might not be something quite so simple like this. Okay? But in this assignment, it's good to practice like this because there is a real function that generates the data. So like in this notebook here, if you've read through it, we've got a function that has a square, a quadratic. So there's really only one feature here, x. But we have 3 terms of x. We have x to the 0 power, x to the 1 power, and x to the squared power. Okay. So given x, we can find out y. So if we didn't add any noise, run through this notebook here. So let's restart the kernel, clear all cells. Let's run everything above this. So here, it is worthwhile understanding this because we do the same thing on your assignment. Here we've got a function that is the reality of what we're going to try to discover, but we've added some noise, right? So this happens in the real world as well. So if you take measurements, there's lots of sources of noise of the measurement. So I mean, your instruments might be a little bit noisy. They might not be able to measure the thing you're trying to measure exactly. The real world might be adding noise before you even measure it. Right? So we simulate some noise here by adding in some numbers. So we use a normal distribution, which means that the values that are generated by rand n have a mean of 0 and a standard deviation of 1. So they're values that can be positive or negative. They're close to 0 usually. So a standard deviation of 1 means that there's a 66% chance that they're between -1 and 1. Right? If you don't know what like a normal distribution is, you might want to kind of review the notebook that I had on statistics. We talked a little bit about some of those concepts and things. So anyway, that's all we're doing here. So for example, if that was 0, we would be able to see what the sorry, not that. Yeah, that. So here we're actually scaling it. So you get a random normal number with a mean of 0, standard deviation of 1. And by multiplying that by 0, it's just going to be 0. So we're not adding any noise if we do something like that. Right? So that's our actual function, and we actually pick some points that are. Again, we've only got really one feature on this example and on your assignment. So x, right? We're not using real data. We're just using made-up data. But we're also selecting random values for the feature x from -3 to 3 in this case, right? So this real quadratic, I mean that's the actual function, right? But as in a real data set, you'll never get it so that you get exact measurements of the thing that you're trying to fit a regression model to. There'll be some noise around it. So you have to try to find out what the real function is by fitting something that ignores the noise, finds the signal in the noisy data. So we have something like this on our assignment, right? So there's really a true function there, but every point has been randomly perturbed plus or minus a little bit, plus or minus half of a standard deviation of noise here. So, yeah, so I guess I didn't really have to do that. So, again, just to show this, so like for this example here, we know what the true function is, right? But for a real data set, you wouldn't know that. So, but it's good to play around with some made-up data like this so you can get a better intuitive feel for how a regression, how fitting a regression model like this works, right? So like for this or for your assignment, you won't know until I give you the secret function after you're done working on the assignment, what the true function is. But you'll be able to see kind of how well the different approaches and the different approaches to adding regularization do on approximating or figuring out the true function from fitting a polynomial regression to your noisy data. Okay? So anyway, that's how we're starting off with. So we've got a true function. It's really only one feature, but we've got higher powers of the feature, x to the 0, x to the 1, x squared. And we wanted to try and fit a model to that noisy data, the best model that we can. Okay? So you can actually do that with the linear regression from scikit-learn, although you have to do some things by hand. It doesn't support doing like a polynomial regression out of the box. You have to actually generate the higher power features. The polyfit function supports fitting a model of any power that you want directly. Okay, so this is how polyfit works. So if you say, so basically what you're doing when you do a polynomial regression is you have to bring in some knowledge of the problem to say, well, I think that this might be a quadratic model. So we've got something that's varying as the square of my feature. And maybe also as the first power and some constant as well. Right? So when you do a polyfit, so we showed last time we did a polyfit for a degree 1 polynomial, which is just fitting a line. So we only have the slope and the intercept term. So if you want a quadratic, a second degree model, you can say 2 here, and it will fit so there'll be 3 parameters in that case. the one for the x squared, the one for the x to the power 1, the one for the x to the power 0. And again, you can do that for any polyfit, you can do that for any model. So if I think it's a model that varies up to the 8th power of my feature, I can say 8, and I'll get 9 parameters. It'll be in that order. So you get the highest one first, down to the x to the 0, the constant, or the intercept parameter. And as the last one is the order that polyfit. So you can compare this to the true function that we had here. Right? So remember, our true function was 1/2 of the x squared, and then 3/4, and then 3. Right? So 1/2, 3/4, and 3. You can see how well it does. But you'll never be able to get exactly the right model because there's noise in here, right? So this is as close as you could do. This minimized the cost. Okay, and I'm jumping ahead here a little bit, but we're doing the same thing that we did last time for linear regression. So we just need to find these 3 parameters, and we need to optimize them so that they give us the smallest cost. And since there's some noise in here, you can't get a cost of 0. But there will be one set of ABC, or theta, theta 0, theta 1, theta 2. We order them backwards when we do them in this class. So we usually use theta 0 for the constant, or the intercept term, and then and that makes more sense because theta 0 is the x to the 0 power, theta 1 is the x to the 1, theta 2 is going to be the x squared power, and so on. But yeah, so what we're doing exactly the same. Polyfit is doing exactly the same optimization that we talked about last week. So it'll just do the mean squared error, and it will find the values of A, B, and C that gives the smallest cost, which are these in this case. So if you look at the model, again, you'll never be able to exactly, if you don't know what your true model is, you'll never be able to get exactly the model. But you'll see that this optimization will do pretty well. So this is a plot of the true function and the model that polyfit gave us, the ABC that it fit to the function there. So, kind of as an aside, I mentioned this before when I graded the previous assignment. I didn't talk about it too much for people. I mean, some people were still doing the thing. I was mentioning that weren't really using a different set of points. So here, if you try and plot the function that you fit to your data, it'll look strange if you do that for your third assignment. So you will have to do the same thing where you fit a model and then try and plot what your model. So whenever you're plotting a model, you should always plot it as a line. So whenever you're plotting a regression model, it should be a line. Whenever you're plotting data points, they should be plotted as a scatter plot, as separate points. But these points here were in random order. So so here is the, in order to plot the true function, the polynomial fit, we created a new set of points that was actually sorted from -3 to 3, and there was 100 points in that space. So if instead of using that, we had used XH was the original X points, the points that we used to fit the model with. So those are not sorted. I might have to reshape that to do this, but let me see if that works. But yeah, you'll get something like that. So since they're not in any particular order, it's plotting line segments, back and forth. So anyway, so it's always best practice to when you're actually plotting a fitted model like this, you'll want to plot it as using a new set of points that covers the range that you want to visualize your model on. And since it's not, if it's a nonlinear function, it won't do anymore. It's just use 2 points because it's not on a line. So you're going to have a sufficient grid, a sufficient small enough step between the points that you will be able to see the smooth actual curve of the model that was fit to it. All right. So, so I mentioned that if we want to, we can do the same thing with scikit-learn that we just did with polyfit. It doesn't support it directly, so you kind of have to do it by hand. So what I mean by hand is, we've only got one feature x, but I can easily calculate the squared terms of x, so I can turn it into, we have two features. So x squared is just x. That's just the square of each of the inputs. So I could have just created a new array that had the original x and then the x squared feature and done a linear regression using scikit-learn. So it becomes, if I want to do more than like the quadratic, the second power, it becomes a little bit of a bother to do that by hand. So there is something in scikit-learn called polynomial features that will give you all of the combinations of degrees. So this does a little bit more than what I'm implying here. So the polynomial features, if I ask for degree 3, it'll give you the cubed and the squared and the power of 1, power of 0, but it'll also give you the combinations. So if I have, in this case we've only got one feature, but if I had two feature, I'd want the cube and the square and the first power of both of the features, but I'd also want the combinations, like feature 1 times feature 2, the square of feature 1 times feature 2, and so on. And that's, polynomial features will do all that for you. So if you read this notebook, I think we go into some more details on that. But the basic that we're doing here, if we have a single feature, it'll do kind of the same thing as we were implying doing by hand here. So if you get the degree 2 polynomial feature combinations, you'll end up with an array that has the original feature and the square of the feature. Right? So if there's only one feature, you just get the two combinations in this case. But once you've done that, you can just use the straightforward linear regression. You'll get exactly the same result that that the polyfit gave, because the polyfit is doing exactly the same thing that linear regression is doing. It's just using the mean squared error to fit to minimize the cost for the features that you give it. So see, if you compare these, I mean, we get the intercept separated, so that's the x to the 0 power, or the constant power, and then these are going to be the x to the 1 and the x squared power. But again, these should be exactly the same that we got for polyfit, like 0.505 for the x squared term. If you go back and look at, where's polyfit? I did it up above here. There it is. 0.505, 0.763 for the x to the 1 power, and so on. Right. So yeah, question.
So when we use the polyfit or when we use the scikit-learn, can we stick to there's a polyfit?
Well, for this, you should use this method here for the assignment. The one thing that you can't do with polyfit is you can't try the, I guess it wouldn't make a difference for our assignment, yeah, for polyfit, you can't try like the combinations, so if I have two features, polyfit isn't set up, like if I have feature x1 and x2, I might want to do the squares. So I might want x1 squared, so a x1 squared, b x2 squared, c x1, d x2. But you also want the combinations like x1 times x2, that kind of thing. Yeah, now that I think about our assignment, we've only got one feature, so yeah, you should be able to get the same results that you would get for polyfit, but you should use the polynomial features. Probably the main reason why you should use the polynomial features and use a linear regression for the assignment is it'll be a lot quicker to make a pipeline that first puts the stuff through a polynomial features for some degree, and then fits the results of that using a linear regression. So yeah, if you haven't done that on the assignment yet, and we'll have some examples of that later on here, for doing things like a more sophisticated grid search or something like that, it'd be tough to do that with polyfit, but you can do that easily, for example, to find a model with a degree 100 polynomial per set of data, or something like that, using a pipeline. So, okay, anyway, back to this. What was? This is, I guess, kind of the answer to what the stats model that we were doing in the previous assignment. So if you only we were just fitting it to I don't remember. Let me go on here. So why were we doing that there? We were showing just fitting degree 1. Well, I guess the point is what we're beginning to talk about here is that when you're doing what we're doing for the third assignment, you have to bring some knowledge into the problem, right? So, I mean, you could fit a line, you could look at this data and say, well, maybe it's a linear model, right, and fit a line to it, and you'll get a line that's a result there. The thing is that if you don't have some knowledge and kind of know that, that this is really a nonlinear function, I should be trying to fit a nonlinear model to it. You'll never be able to get a very, very good results if your model isn't powerful enough, right? So if the true the reality that's generating this data is nonlinear, trying to model it with a linear model will never give you very good prediction, very good results when you're trying to predict stuff. So yeah, I think that was kind of the point of what we're starting to talk about here, and we do a little bit of that in the assignment. So we start by fitting a linear model, so what's known as an underfit model, to look at its performance, and then we look at more powerful models with much higher power to see how well they can do at predicting, how well they can do it. The cost function overall when you fit it to the data. So yeah, this was what we were talking about here, that if you have two features, so polynomial features is a little bit more useful than what the previous example might imply. So here, if we have two features that we generate data on, if you ask for the degree 3 combinations from polynomial features, you'll get not only the a cubed and b cubed, but you'll get the a times b squared, the a squared times b, and all those different types of combinations. Right? So if you only have a single feature, you could probably use polyfit to do the same stuff. But once you have 10 or 100 features, you wouldn't be able to use polyfitting. You'd have to use something like this, because often combinations like these are going to be useful as well in building a model of some nonlinear data, nonlinear function. So yeah, in this case, when we have 3 features, we end up with 10 combinations in all. Or sorry, 9 combinations of 10 data points. Yeah, 9 combinations. All right, so yeah, let's talk about the learning curves then. So like the second task you're supposed to do on the assignment is you have to actually write a function to show these learning curves here. Okay? So let's make sure everybody understands the purpose of these. So let me just get all these out here. So in this example, we've got the same function. So yeah, I think of anything that we do on this assignment, this might be the most important kind of concept to understand. The concept of underfitting or overfitting a model here. Okay, so this is really the heart of a lot of the stuff that we do for supervised learning in some sort of machine learning problem. So in this case, we've got the same model. So we've got the actual same reality that's generating data and the same noise that we're adding to it that we were just working with before. Okay, so we can see what would happen if we fit a underpowered model, right? So this is really a quadratic function, so a function that has a square that's governing what the output is, right? So we can fit like a linear model, or we could fit a higher polynomial degree model. So we could try to fit overfit. So we go to the other extreme here. So in some sense, you should be able to understand from this example that this is going to be underpowered. It's never going to be good enough to give good predictions, since the actual reality is a quadratic function. But in some sense, this is going to be overpowered. So if we use a really large degree polynomial and fit to that model, we can do that. But the result will look something like this figure here, right? So what we're plotting here is the we just changed the range. That was the only thing we changed from before. So we're only looking at it from -1 to 1 here. So the true function is a degree 2, the polynomial. Well, we don't plot the true function here. We just plot the fit, our linear fit, the quadratic fit, and then the degree 300 fit that we have here. So this figure might not do it justice. I mean, the degree 1 might not look too different than the degree 2 here, but the model, the data really is quadratic here. Right? So the overfit model is probably easier to understand in this visualization. You can kind of see the problem that happens when you overfit a model, when you use a model that's too powerful. So what's happening with the degree 300 polynomial is it wiggles around a lot, trying to go through every one of the data points, get through it. And I mean, in theory, if you kept increasing this, you'd be able to get a polynomial that actually went through every one of the points. Right? The problem with that is that this is modeling, the noise, which is incidental, right? You shouldn't be trying to predict the noise here. You'll get bad predictions. So think of a point, especially here on the end, where it gets really wiggly in order to to go all through these, right? So if I have some data that I've never seen before, so if I have like a data point somewhere here, right? Since the true model is quadratic, we might end up for this value of x, have the value like somewhere around here with a little bit of noise, right? So if I was trying to predict from the degree 1 or the degree 2 polynomial model, I'd be pretty close. My error would be small noise. But if your model is overfit, it will give very bad predictions, especially in some ranges here. So it'll give a really large error prediction for data that it hasn't seen. All right? So that's kind of the essence of an overfit model here. It will have a really low cost on the data that you fit it with because it's going through as close as it can to all the points. But for data that it hasn't seen, it's going to give really bad predictions. You're going to get really bad errors especially like on the ends of the range here. So and I mean, so to go back to the underfit model too, this figure doesn't illustrate it quite as well as it does for overfit, but you can imagine, so if we have like a true function that's a quadratic, or if the true function was a x to the 8th power or something like that. So if the true function was something like that, was more wiggly, if my model is underfit, you'll have similar problems, right? So a lot of places, like trying to model this as a linear model will never be able to get all of we'll have large places where its error is really bad, right, where it's not doing well. So whenever you're doing polynomial regression like this, or whenever you have a model that's a linear fit is not good for it, you do have to do something to try and figure out, well, what is the correct degree of the model, right? So what power do I need the model to be, right? So, and that's where learning curves comes in, right? So you won't ever know what the true reality is for real data, but we can kind of hone in on what is a good power for a model by using learning curves, right? So how do we do that? We'll be using these terms underfitting and overfitting. So if your model is not powerful enough, you'll be underfitting, and it's not going to do well at prediction. If your model is too powerful, also you'll won't do well at predicting data that you haven't seen before. Right? So our goal is always, we want a model that's not only good at predicting, good with the data that we fit it with, that we trained it with, but it should be good at predicting unseen data, new data that it wasn't actually fit or trained with. All right? I had kind of forgotten. I mean, one of the second task you have to do is pretty similar to the stuff here. We did modify what you're asked to do for task 2, but you are supposed to create a function to generate the errors in order to plot these learning curves. Okay, so here. If you look at the way that this works is we plot the learning curves for, in this case, we're starting off with the underfit model. So the linear regression, the degree 1 model for our data that's really quadratic. So our function in reality is a quadratic And what we do when we plot the learning curves, in this version, there's different ways you can do this. We'll see another way later on in the course. But we start off by just taking 1 point of the data. Well, actually, we split it. So we start by splitting the data that we're giving into 2 parts. So 20% we keep back for testing, always for testing with, we call it validation here. And 80% we're going to be generating the learning curves with here. But then among that 80%, the data we call the training data, we start by building a model that only uses the first point. So it only uses a training set of 1 sample to create a model, right? So then we fit a model, and then we calculate the cost. So we're getting the errors just by calculating the mean squared error, but we calculate the errors on the data that we trained it with. So these training errors are the data of how much of the mean squared error was on just that 1 point, the first time we iterate through here that we fit the model with. But we also calculate the mean squared error on all of the 20% of the data that we held back for testing, or what we're calling validation here. All right. So if you think about it, I mean, if I have just 1 point and I fit a model to that 1 point, that 1 sample, we should get and we're just plotting the root mean squared errors, and we're just plotting the error on the data we trained with and on the data that was not trained with, the data that had never seen before. Right? So with just 1 point, it goes through the point. So we get 0 error, but we get a really high error on the validation data. All right? But we build models then with 2 points, 3 points, up to the 80%, right? So if we had so we end up with results up to 1,000 on the training set size here. So I'm trying to remember how big this data was, but oh yeah, it was 10,000. We only show the first 1,000 because it doesn't change too much after 10,000. How did we? Anyway, let me check something here. I'm trying to remember how big that size was. What's the shape of X here? Yeah, 10,000. Okay, well, I can't remember. So yeah, we actually should have had gone up to 800 here. I can't remember how we're limiting the x-axis here, but yeah, I mean everything is mostly not changing once you get past here, past 200 or 400 for the training set size. So eventually we end up getting. This is basically kind of converged here, and that is typically what will happen if you're if you're plotting learning curves for an underfit model, because eventually, again, our truth function is something quadratic. We're fitting a line to it, but if we only fit a line to 1 point or 2 points, so if we have some noise like this, we fit it to 2 points, we might end up with a model like that. If we fit it to like 3 points, then we might get a model like that. So eventually we will get something that's, and it happens relatively quickly for this set of data. So after about 100 or so, or maybe 200 or so, we will be getting about the same model. So adding new points onto this won't change the model very much. So the training error will stop changing. But we'll mostly be getting also the same, since the model, the line isn't changing very much, we'll be getting about the same result when we look at the errors for the unseen data, the validation 200 points that we held back, or actually 2,000 points, I guess, since we had 10,000. But the thing is that for an underfit model, the results, so you can use this error, that the overall goal would be to get a model that is able to get the best possible, the lowest error on unseen data, on validation data. Okay? So this is kind of converged. So we're getting similar results after 200 or so, after the data that we train with is around 200 points. But we end up with a root mean squared error for both of these, somewhere between 0.17, 0.18, and 0.19 for the root mean squared error for the cost. Okay? So that's usually the first question that we want to ask is, is the validation and training errors converging or not? For an underfit model, they will usually converge, and to jump ahead though, they'll converge at a level that's higher than what you can get for a well-fit, for a model that's just right, a Goldilocks model. You don't want something that's underfit, you don't want something that's overfit, you want something that's just right in terms of power to represent the data that you're trying to fit a regression polynomial to. So, so we can look at ask the same thing. Here's an example. This is what you want to do for the assignment is just to make it easy, you can create a pipeline where you first put it into the polynomial features for the degree that's asked for any of the tasks, and then it'll fit a linear regression to it. Once you have a pipeline like that, you can just treat that as if it is a transformer, a scikit-learn transformer. So you can just pass that in to something that expects to have functions like fit and predict, right? And basically it'll when it fits, it'll fit it to here, get the results, and then fit that to there. Then when you ask predict, it will put the data first through the polynomial feature and then predict it using the fitted model, linear regression model that we have. So, oh, that's still running, yeah. So this one might take a little bit of time here. So maybe I should go ahead and get the rest of these running here. So, here we're fitting a degree, we went down to a degree 100 instead of degree 300, but we're fitting a high-powered model that's that's overfit for the data. And here we fit a degree 2, so the actual data is degree 2. Oh yeah, that was all that we had in this notebook here. So, when this one, while we're waiting on that, what we'll see for a model that's overfit, the pattern will look something like this. So for an overfit model, very quickly, the training data will converge, will be able to do really well, right? Because remember, for an overfit model, it's got so much power to wiggle around as needed. It can go through a lot of points, get really close to them, even if I have a lot of points that I'm fitting a model to. So you'll see that the training will come up here and very quickly it'll stop increasing on the error. I can't remember, probably something around 0.10 or something for this set of data here. But I don't know if I have a blue marker here. The problem is that, you know, if we're overfit, for data it's never seen before, it will do awful. So it'll get really high errors, no matter how well it's doing on the data it was fit with. If you ask it to make predictions on unseen data, it doesn't wiggle through those. So you'll see that the error on the validation data stays really high, right? They never converge, they never come close together. All right, let's see. Yeah, there we are. So I ask people to, you know, limit the y-axis. So notice, I mean, it almost kind of came down here, but this didn't really converge, okay? And it takes a little bit of experience maybe to, you know, so you might look at this, especially if you don't limit your axis. So let's show, oh, I can't plot that. So if I didn't limit my axis to 0.3 up here, some of these values are really big. I mean, you know, these are like root mean squares errors of like millions. So really high. So if you plot it without limiting, everything will be squashed down to 0, except up here you get really high errors. Then these errors will be down here. You won't be able to read them. Right? So anyway, yeah, to interpret some of these, you really do need to make certain you limit your y-axis. The goal is I need to see the level at least for my training data. Right? And it basically, after a while, looks like it converges around, you know, a little bit below 0.1. Right? So the data it's trained with, if you ask it to do the error, it can get 0.1, and you know, it can get really good because it wiggles through and fits, goes through as many points as possible when the model is overpowered. But it never really gets good performance on the validation on unseen data. Right? It never converges down to that level. Okay? So that's indicative of an overfit model. But another important thing about this is the level, the performance that you get in terms of the cost on the training data for an overfit model gives you an idea of what might be possible. So for a model that's a Goldilocks model, that's not too powerful but not underfitting, should be able to converge, but instead of converging at a bad, you know, like 0.19 or something, so you don't know that 0.19 is bad. And maybe really the data was linear and that's about the best you could do, right? But here when you overfit a model, this is an indication that, you know, 0.19 is probably not a good performance. I should be able to get a model that's of about the right power that can somewhat approach more like 0.10 overall. Okay, so that's the usefulness of fitting a too powerful model. That it gives you an idea of once I get the right power for the polynomial that I'm going to fit to it, what should be possible to achieve on my error on data, you know, unseen data, on data I'm testing with or validation data. All right. So yeah, we're done with it. So this is what you want to see for a good model. So notice that the training data was about, you know, about the 0.10, a little bit higher, but it got around to that 0.10, maybe a little bit below 0.10 for the overfit model. But you know, we definitely converge here on the validation. We get the same performance. Right? And this was the degree 2 model. And compare this to the learning curves for the underfit model. You know, they also kind of converge, but they're converging at a much higher error, right? So that's indicative that this model is both fitting well, but it's definitely better than the other one. We're able to fit, and we're able to predict on unseen data at 0.10 cost here, a better cost than what we had on the previous one. All right. So yeah, that's a good point. Let me bring up real quickly the assignment. I got maybe 5 more minutes here. So that's about the first half of the assignment, and then the rest of the assignment is on regularization. So I was just going to bring this up just to show it, but just taking a little bit of time to start. So like the first two tasks are to load the data set and to basically to write a function to do in order to calculate the errors and do the same learning curve we had in that example there, although you have to do it in a slightly different way. You're supposed to actually calculate the errors only in the function that you write for the assignment, and then those are returned as a result, and then you plot those by hand. So the example that was given in the lecture notebook was doing the plotting and other stuff all inside of the function. Seem to have slowed down here. Okay, well, yeah, maybe I won't bring that up. So so let me know if there's any questions. So after you do that, so the next tasks after that are to fit an underfit model and an overfit model. So kind of the stuff that we talked about. I think that's like task 3 and 4, right? And then after that, we start talking about regularization. So there's different ways that you can try and make a model that's a good, that's a Goldilocks model that's not too overpowered but not underpowered. One basic tool in that toolkit is regularization. Okay, that'll be a topic Thursday. But the last 2 or 3 tasks are to use some other types of regularization. What was the other one? Ridge and lasso regularization, and try it out. So, okay, yeah, I guess I'm not going to be able to bring that up, unfortunately, but all right. So, okay, finally. Yeah, so let me know if you have any questions on the assignment 3. I'll try and bring that up earlier next time, so Thursday will be the last chance. That's here face-to-face for asking stuff. Some questions, you can send emails if you have questions on the assignment or anything. So we'll cover what we mean by regularization and how it works pretty much on Thursday. All right. Yep. That's it. Thanks. In it there, I guess. Which I guess this isn't going to come up. So.
I have one question.
Sure.
Okay, so I'm trying to do the research part, and I'm trying to fit the model, but every time it comes to fit the model, it says the parameters are invalid for what I've done here.
Yeah. you have to have the name. The name of this can't be just alpha when you created it in. So, but I can't remember exactly what it needs. But you might want to look at that again. So I think you have to prepend like the name of something. Because if you're putting it through a pipeline, I think you have to prepend like the name of the part in there. I'll have to go back and look at my example. Yeah, if you go back and look at the example that we had on the notebook.
Yeah, because when I scroll down here, but instead of doing lasso, you use linear regression
Right.
for the pipeline.
But yeah, this here. So the name on the pipeline of the first thing is polynomial features, and then that passes on the degree. So I think you have to do something similar. So you have to do like the name. It's like 2 underscores, and then the name of the parameter that model is expecting, so that it for the grid search it gives those to the right one in the pipeline. So it's something like that.
Okay.
If you can't figure it out, send me an email. I can get you more details on that. But I'd have to go back and look at the example for the grid
Thank
search.
you.
Yeah.